Hey, what's up? Welcome to another video. In this video, I'll be going through an Edexcel sample assessment exam. This is paper 3, Statistics and Mechanics. There's two parts to this paper. Part A is statistics, part B is mechanics, 5 questions in each. This is a 2-hour exam. You'll need the formula and statistics tables booklet and your calculator. I'll put the timestamps to each question in the description in case you want to jump straight to say question 6. You can just click on the timestamp. And I'll put the paper and the mark scheme links in the description as well. I think that's everything, so let's get straight into the questions.
Question 1 says, the number of hours of sunshine each day, Y, for the month of July at Heathrow are summarized in the table below. So here we have the hours, the groups of hours, and here we have the frequency, so the number of days in each group. And it goes on, a histogram was drawn to represent these data. The 8 to 11 group was represented by a bar of width 1.5 centimeters and a height of 8 centimeters. And part A asks us to find the width and the height of the 0 to 5 group. Okay, so one thing to note just before I get into this paper is that often in statistics and mechanics papers, the questions are quite wordy. So that is something to note because it can be sometimes overwhelming to see these really wordy questions. So just prepare yourself for that. But anyway, so I'm going to go through a general process that you can use when you are given questions asking for the width and the height of histograms. And the first thing I'll say is that it involves ratios. So we can use ratios to help us solve this. So let's have a look at, I'll do a quick sketch of a histogram. So typically on a histogram you have the frequency density on the y-axis and the groups on the x-axis. So in this case we have hours. And on the y-axis, they haven't given us the frequency density, they've given us the height. So they've given us the height of the third group here. So let's draw that in. So they've given us some height for this here. Let's just call that H1 for now. But on the histogram, they would have the frequency density on the y-axis. So we could also label this as FD1, so frequency density 1. And we're looking for the height of the first group here. So let's call that H2. This would also coincide with the frequency density of that group. Now, we can't say that the frequency density equals the height, obviously. But we can use ratios because the ratios of these two things will be equal. So remember that frequency density equals the frequency divided by the width, the class width. So we can say that the frequency density of 1 divided by the frequency density of 2 of the second bar will equal the height of the first bar divided by the height of the second bar. So for part A, that will be the equation that allows us to solve this problem. And make sure you get the heights and the frequency densities around the right way. We can work these frequency densities out. So using this frequency divided by the width, for the first one, the frequency density for this 8 to 11 group will be 8 divided by the class width, which is 8 to 11. So the class width is 3, so that frequency density will be 8 divided by 3. The frequency density for the second group, they've asked us to find, 0 to 5, that will be 12 divided by the width of that group. So the frequency density of that 0 to 5 group will be 12 divided by 5. And we know the height, they've given us the height of this third group here, that was 8 centimeters. And we're looking for the height of the second group, the 0 to 5 group that they've asked us to find. So we will just leave that as H2. So you can see here we've got an equation with one unknown, and that's going to allow us to find that height. So let's do some rearranging here. So if we want to work out these fractions, that's going to be a over 3 multiplied by 5 on 12. So just flip that second fraction around and multiply. This equals 8 divided by H2. So let's do some cancelling here. Divide this by 4, this one by 4. And on the top line we get 10 divided by 9 equals 8 over H2. And then do some algebra, so multiply by H2, multiplied by 9, you get 10. All right, let's just do the whole thing. So 10 times H2 equals 72. And then divide by 10, so H2 will equal 7.2 centimeters. Okay, so that's the height. Now the width, that's a little bit easier because we can just look at the first one. It's 1.5 centimeters for a group of 3. So that's going to be half a centimeter per hour of the groups of the class widths. So for this one, we have a width of 5. So for half a centimeter for each hour, that will be 2.5 centimeters for the width. So this will be 2.5 centimeters. Okay, so there we have the width and the height. And you can use that approach for any type of question that asks you for the height and the width in a histogram.
Part B says use your calculator to estimate the mean and standard deviation of the number of hours of sunshine each day for the month of July at Heathrow. Give your answers to 3 significant figures. Okay, so it says use your calculator, so get your calculator out and you'll have to go to the statistics function. On this TI-83 Plus, it's this button here. I press the statistics button and it brings up this menu. So edit, meaning edit the list that I have. So I need to go to edit, so press enter, and it comes up with these lists, list 1, list 2, list 3, and you can make, I think it just keeps going. But we only need 2 lists. List 1 is for the hours, and list 2 is for the frequencies. For the hours, for the groups, we want to put the midpoints in, and you can see I've already put these in here. So for the hours, we want the midpoints of each group. So 0 to 5 is 2.5, 5 to 8 is 6.5, 8 to 11, 9.5, etc. So what I'm doing is just adding them and dividing by 2 to get the midpoint. And then the frequencies are straightforward. You just need to put those straight into list 2. So once you've got those lists filled out, that's the time consuming part really. Then quit out of that. You need to go back into statistics and then calculations. So calc for calculations. We want a 1 vars stats test, meaning 1 variable statistics, because we have 1 independent and 1 dependent variable, or if you like, really only 1 variable here, which was the hours. 2 variable statistics is where you have 2 independent variables, like a scatter plot, for example. So we want the 1 vars stats, press enter, and then we want to put the lists in. So we've got list 1, and see these little L1, L2 down here. Separate those with a comma, and then we just press enter, and it's going to give us our statistics. So that mean there is the mean for this data, and this sigma x is the standard deviation. Okay, so we just need to go ahead and write those down for part B, and it's set to 3 significant figures. So for part B, we're going to have 6.63 for the mean. So let's just say using calculator, the mean equals 6.63 and 3.69 to 3 significant figures. And so for part B, that's done. One part C says the mean and standard deviation for the number of hours of daily sunshine for the same month in Herne are 5.98 hours and 4.12 hours respectively. Thomas believes that the further south you are, the more consistent should be the number of hours of daily sunshine. State, giving a reason, whether or not the calculations in part B support Thomas's belief. So let's remind ourselves what they were for B. That was 6.63 and 3.69. The mean daily hours of sunshine and the standard deviation. And in Herne, it was 5.98 and 4.12. So for more consistent sunshine, you want a higher mean, meaning you're getting more sunshine, and you want a lower standard deviation, meaning there's less variation in the amount of hours you're getting. So Herne is actually what you would say less consistent than Heathrow, and Herne is actually further south than Heathrow. So this does not support Thomas's belief, because it would be the other way around if so. So we just need to state that in a couple of sentences, and that should be good enough for those 2 marks. So let's go ahead and write something down here. So here's what I've written. Higher mean and smaller standard deviation suggests more consistent sunshine, as I explained before. Herne is further south and has lower mean and higher standard deviation. This does not support his belief. So I think that would be good enough for 2 marks. Part D says, estimate the number of days in July at Heathrow where the number of hours of sunshine is more than 1 standard deviation above the mean. So this is going to involve using the calculations from B again, figuring out how many hours is 1 standard deviation above the mean, and then finding the proportion of days in the month above that. So let's get started on that. So for part D, we firstly want to work out what is one standard deviation above the mean. So all we need to do is add 3.69 to 6.63. And for that, we get 10.32 hours. And now I just want to take a quick look at the table. So 10.32 hours, that's going to fall in the 8 to 11 group. So we know already there are 5 days higher than that. So these groups are 11 to 14. 5 days fall in those two groups. But we don't yet know the proportion of days in this group above 10.32. So that's the next thing we're going to have to work out. To do that, we take the maximum in that group, which is 11, subtract 10.32, and divide by the width of that group, or how many hours in that group. So 8 to 11, that's 3 hours. So that will give us the proportion above 10.32 in that group. So let's quickly put that into a calculator. I'll clear that off. 11, take 10.32, divide by 3, and we get 0.226 recurring. And then multiply by the frequency of that group, or the number of days in total in that group. Multiply that by 8, and we get 1.81, which is approximately 2 days. Okay, so we've got the 5 days above 10.32 hours plus the 2 days within that group. So therefore we can say there'll be about 7 days above one standard deviation. About 7 days, one standard deviation above the mean. And that was part D. Part E says Helen models the number of hours of sunshine each day for the month of July at Heathrow by a normal distribution with a mean of 6.6 and a standard deviation of 3.7. And the question asks, use Helen's model to predict the number of days in July at Heathrow when the number of hours of sunshine is more than one standard deviation above the mean. Okay, let's get started on E. So I'm just going to write that down before I forget. So it was N, normal distribution with a mean of 6.6 and standard deviation 3.7. So one standard deviation above the mean, that's going to be 6.6 plus 3.7. And that equals 10.3. So if we were looking at a normal distribution, we'd have the mean. That's a terrible drawing, by the way, but you get the idea, and 10.3 out here somewhere, and we want the area above that. So we're going to be able to use the normal cumulative distribution function on our calculator for that. So bring up your calculator, and there should be a distribution button somewhere. So on this TI-83, it's above the vars key. So I need to go to second function vars, and it brings up this list. Normal CDF is what I want. So go down to 2, press enter. And the syntax for this is the lower value, the higher value, and then the mean and standard deviation. So my lower value here is 10.3. The higher value is the maximum. So usually put in just any large number, usually 9,999 will do. And then the mean 6.6 and the standard deviation of 3.7. Bracket and enter. And that'll give us the proportion of days in July above one standard deviation. So we need to multiply that by the number of days in July, 31, to get the number of days. So 4.91, about 5. So I'm just going to write that function down and my answer. There you go. And then we multiplied that by 31 to get the number of days, which was approximately 5 days. So that was for part E. Part F says use your answers to part D and E to comment on the suitability of Helen's model. So let's compare the answers from D and E. So using our data, we got about 7 days, one standard deviation above the mean. With Helen's model, we got about 5 days. So that's quite a big difference. So 5 is less than 7. And you could use the decimal numbers there to give a bit more accuracy. But 5 is less than 7, so therefore the model might not be suitable. Just fitting my answer in there, and that was question 1 for a total of 13 marks. Question 2 says a meteorologist believes that there is a relationship between the daily mean wind speed, W knots, and the daily mean temperature, T degrees centigrade. A random sample of 9 consecutive days is taken from past records from a town in the UK in July, and the relevant data is given in the table below. So here we have the temperature and the wind speed. The meteorologist calculates the product moment correlation coefficient for the 9 days and obtained R equals 0.609. Part A asks, explain why a linear regression model based on these data is unreliable on a day when the mean temperature is 24 degrees. So if we look carefully at this table, we have a minimum of 13.2 and a maximum of 19.3. So 24 would be outside of that range of data, and we would have to use extrapolation, making the linear regression model unreliable for that temperature. So we just need to state that in a sentence. So for part A, we can say something like 24 degrees. 24 degrees lies outside the range of data and requires extrapolation. Part B asks, state what is measured by the product moment correlation coefficient. So this is the strength of the linear relationship between the two sets of data. So you'd get a scatter plot with the data points. So this might be temperature and wind speed. And you can analyze that data and try to find a linear relationship between them. And R measures the strength of that linear relationship. So if the data is all over the place, R will be quite low. But if it does have a trend, like a linear trend, then R will be quite high. So 0.6 is a bit higher than 0.5, so it's all right. But let's state what R is for part B. So I'll say something like the product moment correlation coefficient measures the strength of a linear association between two variables denoted by R. So that should be enough for 1 mark. Part C asks, stating your hypothesis clearly, test at the 5% significance level whether or not the product moment correlation coefficient for the population is greater than 0. So for part C, we need to set up a hypothesis test. I'm just going to start by writing down R. So that's 0.609. And our hypothesis is that the population correlation coefficient will be 0. So HO, the null hypothesis, rho, or the Greek R. I'm terrible at writing Greek letters, but there you go. Mathematicians love Greek letters, as you know. And the alternate hypothesis is that rho is greater than 0. The population R. Okay, and we're at a significance of 5%. So alpha is going to be 5%, or 0.05. And our sample size, N, is 9. Okay, so now we can look up the critical value for a sample size of 9 and alpha of 5%. So you'll get these tables. You'll have access to these in the exams. Hopefully you've been using these in your A-levels. So here's the product moment coefficient. This is on the critical values for correlation coefficients page. And we look at the sample size first, N, and then go across to the correct significance level. And we get a critical value of 0.5822. So we can go and write that down. So critical value equals 0.5822. And I love diagrams, so I'm just going to give a quick illustration of what we're talking about here. So the hypothesis test, again, that's a terrible normal distribution, but there you go. The hypothesis is that the mean R is 0. And we're testing if it's greater than 0, so we'd expect the values to fall somewhere below a certain range. And the critical value we've found at the 5% significance level is 0.5822. So we'd expect, if it was 0, for the values to fall in here somewhere. But we have an R of 0.609, which is actually over here, greater than our critical value. Which means, based on our hypothesis test, we have evidence to reject the null hypothesis. So we can state that to finish this off. So the decision is going to be that R is greater than the critical value, or C, therefore reject the null hypothesis. And there is evidence that rho is greater than 0. Okay, so that was part C. Part D says, using the same 9 days, a location from the large dataset gave a mean temperature of 27.2 and a mean wind speed of 3.5. And part D asks, using your knowledge of the large dataset, suggest giving a reasons the location that gave rise to these statistics. Okay, so it's using the same 9 days as these ones. Now, in the large dataset, you should be familiar with the 8 locations in there. There are 5 in the UK and 3 outside of the UK. Given that this is the same 9 days, I'd suggest it wouldn't be in the UK because given these temperatures from the UK, This is a higher mean. So just looking at the temperatures, I'd suggest this isn't in the UK. So that narrows down the locations to the 3 cities outside of the UK in the large data set. And they are Jacksonville, Beijing, and Perth. Now you need to think about the seasons. And maybe you're familiar with some of the data in there as well, but think about Perth in July. That's actually in the middle of winter. So I'd say Perth would not have such a high mean temperature. And Jacksonville is a port city. So if you remember that map, I'll pull the map up quickly. So remember, this is the map from the large data set. These are the 5 locations in the UK, and these are the 3 outside of the UK. I've already eliminated Perth. Jacksonville is a port city, and Beijing is an inland city. So I'm going to get rid of this now. That's enough reminders. But keeping in mind what would happen in a port city, the wind would be stronger. So due to this low wind speed, I'd suggest this data probably belongs to Beijing. So I'm going to go ahead and write that down in a couple of sentences. So for part D, okay, so probably not within the UK, too hot. Locations outside the UK are Perth, Jacksonville, and Beijing. I would suggest Beijing with summer in July and not much wind, being an inland city. Okay, that was part D, and question 2 for a total of 6 marks. Question 3 says a machine cuts strips of metal to length L centimeters where L is normally distributed with standard deviation 0.5 centimeters. Strips with length either less than 49 centimeters or greater than 50.75 centimeters cannot be used. Given that 2.5% of the cut lengths exceed 50.98 centimeters, part A asks, find the probability that a randomly chosen strip of metal can be used. Okay, so for part A, we're told it's normally distributed, which is handy, and we're given the standard deviation. The main problem here is they don't give us a mean, so we're going to have to find the mean in order to find the probability that the strip is between these 2 lengths. So there's a few ways we can find the mean, but let's get started on part A. So let's just write down what we know just to summarize it. It's always useful to summarize the information so you can see it clearly. So standard deviation is 0.5, and they've told us that 2.5% of the cuts are greater than 50.98 centimeters. And also that the lengths of metal are normally distributed with some mean that we don't know yet, and the standard deviation of 0.5. Okay, so how do we go about finding the mean? One way to do it is with a z-score. So we know that the z-score equals the value we're given, take the mean, divided by the standard deviation. We can find the z-score for this percentage. So I'll use a diagram just to explain in a bit more depth. So if we have a normal distribution, and we have the mean here, whatever it is, and then we have this length, 50.98. This proportion above 50.98 is 2.5%. And we can find the z-score at this particular point on the normal distribution, either using the tables or the calculator. So one way to do it with the calculator is use the inverse normal function. So find the distribution menu on your calculator, and it'll come up like this, and it'll have an inv norm. So I'm going to go down to inv norm and press enter. And if I'm looking for a z-score, I just need to know what's below that z-score. So if there's 2.5% above the z-score, that means there's 97.5% below it. So I just need to put in 0.975, and that's going to give me the z-score for that place on the normal distribution. So that's telling me it's 1.9599, or basically 1.96. So the z-score at that place is 1.96, and this is going to equal the value they've given us, 50.98, subtract the mean, divided by the standard deviation. Okay, so that gives us a nice equation that we can solve for the mean. So let's go ahead and multiply by 0.5, and then we'll have 50.98 take mu on the right hand side, and then rearrange this so I have mu by itself on the left. So add it to this side, subtract all this from the right hand side, so I'll have mu equal to 50.98 subtract 1.96 times 0.5. So let's go ahead and put this into a calculator to see what we get. So we've got 50.98 subtract 1.96 times 0.5. and we get 50. So a nice even 50 centimeters for the mean. Okay, now it's going to make finding that probability fairly easy. So we just need to use the normal distribution function on our calculator, or that's the way I like to do it. So I'll just remind myself of the boundaries. So we're looking for between 49 and 50.75. So that'll be my lower bound is 49, my upper bound is 50.75, my mean is 50, and my standard deviation is 0.5. If I put that into the calculator using the normal cumulative distribution function, it's the second one on my menu there. Put in the lower boundary, upper boundary, mean, and standard deviation, and I get 0.91044, about 0.91044, etc. And I'm going to round that off to 0.91 or 91%. So 91% of the cuts can be used that fall between 49 and 50.75. So that's part A. Part B says 10 strips of metal are selected at random, and it asks find the probability fewer than 4 of these strips cannot be used. Okay, it's important to pay attention to the language used here. Fewer than 4 means less than 4, not equal to 4. So this is actually going to be 3 or less, the same thing. So let's start part B down here. Now this is going to be a binomial because either the strip can be used or it cannot be used. So the probability of an unusable strip is going to be 1 take the probability of a usable strip, which we found in part A. So this is going to be 1 take 0.91, which is 0.09. So the probability of getting an unusable strip is 0.09. And we want the probability that the number of strips is less than or equal to 3. X being a binomial distribution with a sample size of 10 and probability of success of 0.09. So to find this, we can use our calculator using the binomial function, binomial cumulative distribution function. Now on my calculator, again, that's in the distributions menu. So if I go into distributions, it gives me this list, and I go down until I get to the binomial CDF cumulative, because I want more than just one probability. So my syntax for this is the n value, or the sample size, then the chance of success, so 0.09, and then the value that I need to get up to, so it's up to 3. So I can put 3 there. So the syntax in your calculator might be different to that. Just check which order you need to put those numbers in. Press enter, and I get an answer of 0.9911. So let me just write down what I put in, and then write down the answer. So it was 0.9911 about, and that kept going. Let's just double check, 9166, etc. And I'm going to round that off to 0.991. And they didn't specify a degree of accuracy, so you could round off or just leave the answer as is. So that's part B. Question 3, part C says a second machine cuts strips of metal of length x centimeters where x is normally distributed with standard deviation 0.6 centimeters. A random sample of 15 strips cut by the second machine was found to have a mean length of 50.4 centimeters. And part C asks, stating your hypothesis clearly and using a 1% level of significance, test whether or not the mean length of all the strips cut by the second machine is greater than 50.1 centimeters. And this is for 5 marks. Let's go ahead and get started on part C down here. So again, I'm just going to state the information. I find this really useful when I'm starting off a question, just to summarize what we know. And it helps to clarify what I'm actually trying to figure out. So the standard deviation was 0.6 centimeters, the sample size was 15, and the sample mean was 50.4 centimeters. And we're trying to do a hypothesis test. So hypothesis, and our hypothesis is going to be, well, the null hypothesis, or H0, is going to be that the mean equals 50.1 centimeters, and the alternate hypothesis, or H1, is going to be that the mean the population mean is greater than 50.1 centimeters. And alpha is 1% or 0.01. Now it's important to distinguish between a normal distribution with data values and a normal distribution with means. The main difference being that data values will have a standard deviation and a normal distribution of means will have a standard error of the mean. So it's still a measure of spread, but we work it out slightly differently. So the standard error of the mean, or SEM for short, is the standard deviation divided by the square root of the sample size. Now there's a really good video by Khan Academy explaining why the standard error of the mean equals that. I'm not going to explain it now. I'll leave you to go and research that if you're wondering, or maybe you already understand it, so that's good. So when we're talking about a distribution of sample means, we use this rather than the standard deviation. So in order to test this hypothesis, we're going to see what proportion of sample means would fall above 50.4 on our normal distribution and see if that's significant at the 1% significance level. And I'm just going to draw another diagram because I love diagrams, even though I'm terrible at drawing normal distributions on here. So we're testing if this mean is 50.1. We got a sample mean of 50.4. And we're looking for the proportion of means above that. Oh, and we should also state that these sample means are normally distributed, and we're assuming the mean is 50.1, and the standard error of the mean is going to be that standard deviation squared, meaning the variance, over the square root of 15. So that would be our model for our normal distribution. So to find that proportion, we can use the normal cumulative distribution function again on our calculator. And our minimum value is going to be 50.4. Our higher value, any large number, typically 4 nines will do. And then our mean is 50.1 and our standard error of the mean is 0.6 on the square root of 15. So if we put that into a calculator, it should give us the proportion above that. So 50.4 maximum value, mean, and standard error of the mean, 0.6 divided by the square root of 15. Enter, and we get 0.0264 approximately. So 0.0264. So that's the proportion there. Now at the 1% significance level, we do not have evidence to reject the null hypothesis. I should state this is our p-value. So our p-value is greater than alpha. Therefore, we fail to reject the null hypothesis, and the evidence suggests mu is not greater than 50.1 at the 1% significance level. So I'm going to state that to finish this off. Okay, there you go. Make sure you always summarize your answer at the end. And that was part C and the final part of question 3 for a total of 12 marks.
Question 4 says, given that the probability of A equals 0.35 and the probability of B equals 0.45 and the probability of A intersect B equals 0.13, find for part A the probability of A complement given B complement. So this is a conditional probability that B complement happens. Okay, so let's firstly write down the formula for conditional probability for part A. So that looks like this. So if we're looking for the probability of A given that B happens, then the formula for that probability looks like B complement A, sorry, B intersect A divided by the probability of B. Okay, so if you're wondering where that formula comes from, it's actually a rearrangement of the fact that the probability of B intersect A, or the probability of B and A happening, is the probability of B multiplied the probability of A given B happened. So it's fairly straightforward. Therefore, we can say the probability of A complement given that B complement happened, probability of B complement intersect A complement divided by probability of B complement. I've just added a complement to all of that. So there's the formula that's going to help us find this probability, and we need to find these. So the probability of B intersect A complement we'll need to work out. The probability of B complement is just the inverse of the probability of B. So probability of B not happening will be 0.55, so that's not going to be difficult. For this one, we'll need to do a little bit more work to work it out. So we need a Venn diagram. Well, you don't need a Venn diagram, but it will help me to explain and hopefully help your understanding. Okay, so there's my event A and event B, and we have the probability of those. So firstly, we actually need to work out the probability of A union B. So that's the two events together. And that's going to be the probability of A plus the probability of B. Subtract this intersection in here, so you're not double counting it. And they've told us that as well. They've told us the intersect is 0.13. Okay, so if we work that out, 0.8 minus 0.13, that's 0.67. Okay, so that's that area in here. So probability of those things. And we want the area outside. Well, how do I work out this area outside here? Well, I just need to do 1 minus this. So we can say that the probability of B complement intersect A complement is going to equal 1 minus 0.67, and that will be 0.33. Okay, so now I have the probability of B complement intersect A complement, so that was again the area outside of those two events, or the probability of neither of those events happening. And I have now the two parts of my formula, so I can go ahead and work out the probability of A complement given B complement happened is 0.33 divided by 0.55, and put that into a calculator. 0.33 divided by 0.55, I get 0.6 for my final answer. Okay, let's go back to the question. Okay, so part B says explain why the events A and B are not independent. When you're talking about conditional probability, if we have the probability of A happening given B happened, if they're independent, B should have no effect on A. So in effect, this conditional probability should not be different to the probability of A happening. Also, for independent events, the probability of A intersect B should be the probability of A multiplied by the probability of B. So there's a couple things we could do, and you need to pick one method and be able to show why they're not independent. Okay, so I'm going to choose the idea that the probability of A complement given B complement happened should be the same as the probability of A complement. So the probability of A complement given B complement happened equals 0.6. Probability of A complement equals 1 minus 0.35 is 0.65. So therefore, complement given B complement does not equal the probability of A complement. Therefore, events are not independent. So you can clearly see that one event is affecting the outcomes of the other event. Okay, question 4 goes on. It says the event C has a probability equal to 0.2. The events A and C are mutually exclusive, and the events B and C are statistically independent. Part C says draw a Venn diagram to illustrate the events A, B, and C, giving probabilities for each region. Okay, so we need to draw a Venn diagram, and we need to know what these mean: mutually exclusive and statistically independent. So mutually exclusive means that A and C cannot happen together, so there's no probability of A intersect C. And statistically independent just means they're independent, basically. So probability of C happening does not affect B happening, and vice versa. Alright, so let's get started on our Venn diagram. Okay, so here's A. Now C is mutually exclusive, so that's going to be the one on the end. B will intersect with A, and then C will intersect with B. So A fairly intuitively, B and C in a row like that. And we need to start filling in these probabilities. So we know the probabilities of A and B and C. So A and B were given at the start of the question, C was given for this part. And we know the probability of A intersect B. So that could be the first thing we actually put in. So that intersection is in here. I've done these a little bit small, but that's in here, 0.13, that intersect. And then we can work out what goes in this circle for A. So the probability of A was 0.35. So what goes inside this circle is going to be 0.35 minus 0.13. So that's going to be 0.22. And then if we were to go over to this one, B or C, we can't fill those in yet because we need this intersect for the probability of B intersect C. And we can work that out because if events are independent, the probability of them both happening, so the probability of B intersect C, is their probabilities multiplied together. So the probability of B multiplied by the probability of C. So that's when events are independent. Probability of B, that was 0.45 from the start of the question. Probability of C was 0.2. And if we multiply those together, we get a probability of 0.09. Okay, so that was probability of B intersect C. And that goes right in here on our Venn diagram. Okay, 0.09. Now we can go ahead and fill in the rest. So the probability of B was 0.45. We need to subtract 0.13 and 0.09. That leaves us with a probability of 0.23. And then probability of C was 0.2. Subtract 0.09, that's going to be 0.11. Okay, almost finished. We also need the complement of all of this. So what's outside of these events? Always in a Venn diagram. So in other words, this is the probability of A or B or C happening, or the union of all of those. So that's everything in here. If we just add up all those numbers, 0.22 plus 0.13 plus 0.23 plus 0.09 plus 0.11, we get 0.78. And therefore the complement of all of that is going to be 0.22. And so now we've completed our Venn diagram and we're done. Question 4, part D says find the probability of B union C complement, or the complement of B union C. So in other words, find the probability of B union C not happening. Okay, so let's go down here and start on part D. Okay, so we're looking for the probability of B union C, or the complement of B union C. And remember, we're still talking about these events up here. These A, B, and C events, so we can use this same Venn diagram to interpret this. The probability of B happening is everything inside this circle, and the probability of C happening is everything inside this circle. And the union of those, the probability of the union is everything inside both. So B or C, we need all of those probabilities in there. Therefore, the complement of B union C is everything outside of those two circles. So all we really need to do is look at this diagram. We've got 0.22 as the probability of A but not B happening, and then we've got a 0.22 probability of none of these events occurring. So the probability of B union C complement is going to be 0.22 plus 0.22, which is going to be 0.44. And you might want to make a note that you've used part C for your interpretation of that, but that should be enough for the 2 marks for that question. Probably 2 marks because you need to understand what that notation means, and you also need to interpret the Venn diagram or use some kind of working out to get to your answer. So there you go, that's part D, and that was question 4 for a total of 10 marks.
Question 5 says a company sells seeds and claims that 55% of its pea seeds germinate. Part A asks, write down a reason why the company should not justify that claim by testing all the pea seeds they produce. Well, if they tested all of the pea seeds, they would destroy them all in the process of testing them. They'd have nothing to sell, and therefore they wouldn't have a business. Hopefully fairly straightforward reasoning there for part A. They would have nothing to sell. And you can flesh that out a little bit more if you like. The main reasoning behind that question, I guess, is to point out that statistics are important to businesses and everyday life, and businesses do need to test their claims that they put in their packages to sell their products, and they can't obviously do it by testing everything, so they do need to use these methods that you're learning in A-levels in order to justify their claims. Part B says a random selection of the pea seeds is planted in 10 trays with 24 seeds in each tray, and asks, assuming that the company's claim is correct, calculate the probability that in at least half of the trays, 15 or more of the seeds germinate. So before I get started on this, I just want to point out when they say, assume the company's claim is correct, they're talking about this 55% up here. 55% of the seeds germinate. That's the company's claim. So we're assuming that's correct, and we need to find this probability. So we're going to have to do a couple of binomial calculations. So I'm going to split this into the individual trays and then all of the trays. So I'm going to look at one of the trays, the probability of 15 or more of those seeds germinating, and then find the probability of that happening in half or more of the trays. Okay, so let's find the probability of an individual tray getting 15 or more germinating. So for an individual tray, we've got 24 seeds, so the sample size will be 24. Our probability of success is 0.55, as they've said, and this is going to be a binomial distribution. So we need to put that in our notation as well. So we're looking for the probability of an individual tray, 15 or more seeds germinating. So we can write that as x greater than or equal to 15. Now the function in my calculator only does less than a certain number, not greater than. So I'm going to convert this to 1 take the probability of x less than or equal to 14. So those two things are equivalent. I hope you can see why. If you're looking at greater than or equal to 15, this is going to be the inverse of less than or equal to 14. So I'm going to use the binomial cumulative distribution function, and the syntax on my calculator looks like this. So n, p, and the x value we're going up to. Yours might look different to that. Just make sure you understand if you are going to use this, how to use it properly. So to find this probability, I'm going to do 1, take that probability, and I'm going to work that out using my calculator and this function. So it's 24, the p-value 0.55, and the x value I'm going up to is 14. So if I put that into my calculator, it'll give me the probability I'm looking for. So I need the binomial function, it's down here, cumulative, and enter the values, and then 1 take that answer. So I get a probability of about 30%, 0.2991. So that's the probability of getting 15 or more seeds in one tray. Now I'm going to look at all 10 trays. So 10 trays, I've got my probability of success. The sample size is 10. P is 0.2991. And again, just show that you understand this is a binomial distribution using the correct notation. And so now we want at least 5. So that's going to be the probability of 5 or more. And again, I'm going to flip this around and do 1 take the probability of x less than or equal to 4. Just so I can put it into my calculator more efficiently. So this is going to be on my calculator. The syntax will be 10, 0.2991, and 4. And if I do 1 take that, it should give me my answer. So 1 take binomial 10, and I might use the answer from my previous calculation rather than putting that in myself, and then 4, and enter. And it gives me a probability of 0.14877. So 0.14877, which rounds off to 0.149, so about 15%. So just to give a bit of context, let's just go back to the question again. So the probability that they had half or more trays with 15 or more seeds germinating was about 15%. That's what we'd expect if that claim was correct. Part C says write down two conditions under which the normal distribution may be used as an approximation to the binomial distribution. So hopefully you've seen that before. It's generally when n is large enough and p is close to 0.5. There are other conditions which involve working out np and nq, and they need to be greater than 5. That condition is used to ensure that the mean is far enough away from the minimum maximum of the normal distribution. But I think for C, they're going to be happy enough with saying that n is large and p is close to 0.5. And you can write those in more detail if you wish. Part D says a random sample of 240 pea seeds was planted and 150 of these seeds germinated. So they've done a test and they have 150 seeds germinating. And part D asks, assuming that the company's claim is correct, use a normal approximation to find the probability that at least 150 pea seeds germinate. So again, we're assuming this 55% is correct, and we're using a normal approximation this time. So let's get started on part D. Okay, our n, our sample size is 240. Our probability of success, again, 0.55. Now, in order to use a normal distribution, we need a mean and a standard deviation. Now, when we're going from a binomial to a normal distribution, the mean is the expected value. So the expected value is the sample size multiplied by the probability of success. So that's n times p. And you know this is true if you think of a coin flip, for example. If you flip a coin 4 times, probability of success of, say, heads is 0.5, you'd expect to get 2 heads. So this is pretty straightforward. So this is going to be 240 multiplied by 0.55. And if we do that calculation, we get 132. And the standard deviation of a binomial is the square root of the sample size multiplied by p multiplied by q, q being the probability of failure. So this is going to be the square root of 240 multiplied by 0.55 multiplied by 0.45. So that's just 1 take p. So the square root of, let's put that into our calculator, 240 multiplied by 0.55 multiplied by 0.45 equals 59.4. And I might leave that as a square root to save me writing out the decimals. And remember, we're approximating this binomial with a normal distribution. So make sure you use that notation to show that you know what you're doing. And we're looking for the probability that we're getting more than 150 pea seeds germinating. So the number of germinated pea seeds will be greater than or equal to 150. And there's an important step in here. When we go from a binomial to a normal distribution, we need to use what is called a continuity correction. So I'll write that down, continuity correction. And this basically accounts for the fact that a binomial distribution is discrete probabilities and a normal distribution is a set of continuous probabilities. Actually, I might pull up a binomial distribution just to explain that in a little bit more detail. Okay, so I've got my binomial down here. So we're going from a binomial to a normal, which is smoothing out those bars. And the continuity correction accounts for the fact if we take some value, let's say, I don't know, 120 or something, if we're looking for the probability of, say, less than 120, which would be all of this in here, on the binomial, you would be missing out part of that bar. But on the normal distribution, we actually kind of use half of that bar to calculate the probability. So the continuity correction adds on or takes away half depending on whether you're doing greater than or less than or whichever type of calculation you're doing. And there's a great video on the reasoning behind the continuity correction, which I'll link in the description. But all of that is to say that we need to change this probability from greater than 150 to x being greater than 149.5. So it's no longer greater than or equals to, it's only greater than, and this is the continuity correction. Make sure when you're going from a binomial to a normal approximation, you're using that. Okay, so now we're looking for the probability that we're getting more than 149.5 in this normal distribution, and we can use our calculator for that. We can use the normal cumulative distribution function. And I'm just going to draw another diagram because, as I've already said, I love diagrams. So if we had a normal distribution with a mean of 132, remember that was our expected value, and we're looking for greater than 150 or 149.5. So we're looking for this proportion of the normal distribution up here. And we have our mean and standard deviation, so this shouldn't be too difficult. So as I said, I'm going to use this normal cumulative distribution function, and my minimum will be this 149.5. My max is the maximum amount. My mean is 132, and my standard deviation is the square root of 59.4. Okay, so if I put that into a calculator, go to the distributions menu, normal CDF, and put in those amounts, it should give me a proportion. 132 and the square root of 59.4, and I get a proportion of 0.01158. So 0.01158, etc. Okay, so about 1%. So the probability of the number of seeds germinating being greater than 150, we've worked out to be about 0.1158. So that was part D. Part E says, using your answer to part D, comment on whether or not the proportion of the company's pea seeds that germinate is different from the company's claim of 55%. So for part D, we got about 1%. That's quite low. They did a sample, they got 150 pea seeds germinating, and the chance of that happening or greater than that is about 1%. So I would say that's fairly good evidence to suggest this claim is probably wrong, and maybe it needs to be increased. But we don't have to suggest that. All we need to say is it suggests the claim is not accurate. So for part E, reiterate your answer to part D, state it's quite low, and then finish off your answer. So we had a 1% chance of that happening, which is a low probability. This suggests that the claim is not accurate. So that should be enough for 1 mark for part E. And that was question 5 for a total of 9 marks. Okay, we're on to section B now. We've left the statistics behind and we're on to mechanics. And before we get started, it gives us this note: unless otherwise indicated, whenever a numerical value of g is required, take g equal to 9.8 meters per second squared and give your answer to either 2 significant figures or 3 significant figures. Alright, so that might come in useful. And question 6 says, at time t seconds, where t is greater than 0, a particle p moves so that its acceleration a meters per second squared is given by a equals 5ti minus 15t to the power of a half j. And then it says when t equals 0, the velocity of p is 20i meters per second. And the question asks, find the speed of p when t equals 4. We're looking for speed, and we're given an equation for acceleration. Now, in order to get from acceleration to velocity or speed, we are going to have to take the integral of this. So anyway, let's get started down here. So remember that velocity is the integral of acceleration. The same as acceleration is the derivative of velocity. So we're going to have to integrate this expression here. So let's get started on that. So the integral of a with respect to t is going to equal the integral of this expression. So 5t, let's just write it out again, minus 15t to the power of a half j dt. Okay, so we can use the power rule for all of this. So this is going to be 5t squared on 2. And remember, I and j are like constants, so we can just leave those as is. And then 15t to the power of a half, well, that's going to be 15 divided by 3 on 2. Remember, we add 1 to the power and then divide by that number. So 15 divided by 3 on 2, that's like 15 times 2 divided by 3. And then 15 divided by 3 is 5 times 2 is 10. So this 15 is going to become 10. And then we've got t to the power of 3 on 2 j plus some constant c. Okay, so we've integrated that expression. And remember, they told us when t equals 0, the velocity
is 20 meters per second. So this is the velocity here. So we can use that information to find c here. So when t equals 0, v equals 20 meters per second. So therefore, what would c equal? Well, if t is 0, these two terms would cancel. Anything multiplied by 0 is 0. So they both cancel out, and we would just be left with c equal to the velocity, which they've told us is 20 meters per second. So c therefore must equal 20 meters per second. Okay, so therefore we can say velocity equals 5t squared on 2 minus 10t to the power of 3 on 2 j plus 20 meters per second. All right, and go back to the question again. What were they asking? They were asking for the speed when t equals 4. So let's firstly find the velocity when t equals 4. So when t equals 4, v is going to equal 5 times 16 on 2 minus 10 times 4 to the power of 3 on 2 plus 20 So now we can just go ahead and simplify this. So 5 times 8 basically, that's 40 minus 4 to the power of 3 on 2. Well, that's like 4 cubed and then the square root of that. So 4 cubed is 64, and then the square root of 64 is 8. So 10 times 8, that's going to be 80. J, I forgot the J up there, 80J plus 20I, which simplifies to 60I minus 80J. So that was the velocity, and that would be meters per second. And then remember that velocity is speed with direction, so for the speed we need to take this direction out of it, so the I and the J need to go. In order to get rid of them, remember they are the vertical and horizontal vectors of velocity. So if we think about it like a right angle triangle, this would be I down here, this would be J, and we are looking for this vector or this length here. So how do we find the speed? We use Pythagoras' theorem. So we say speed is going to be the whatever this length is. So this is 60, this is 80. So we need to take the square root of 60 squared plus 80 squared. Or let's just put that into a calculator. The square root of 60 squared plus 80 squared, bracket 100. So 100 meters per second for the speed. And that was question 6 for 6 marks. Question 7 says a rough plane is inclined to the horizontal at an angle alpha where tan alpha equals 3 on 4. A particle of mass m is placed on the plane and then projected up a line of greater slope of the plane. The coefficient of friction between the particle and the plane is mu. The particle moves up the plane with a constant deceleration of 4/5g. And part A says find the value of mu. Okay, so let's start off with a diagram. So let's just try to picture what's going on here. So we've got our ground and then some height and then our slope here like this. Now the angle of the slope is alpha. And by the way, when they say projected up a line of greatest slope of the plane, that means it's effectively going along the ground of the slope. So it's not going like some angle to the slope. What I've drawn here is a right angle triangle. The particle, let's just draw a box. Even though it says particle, boxes are easy to represent. Now let's talk about the forces acting on this particle. I guess the most obvious one to start with is gravity. So the force due to gravity goes straight down, and that is the mass of the object times gravity. So this is going to be mg. And
that can be split up into two components. You can have the perpendicular aspect of it. So you've got a force perpendicular to the surface that it's moving along, sometimes called the perpendicular force. And then you have the force parallel to the surface it's moving along, sometimes called the parallel force. And we can figure those out, or at least we have, expression for those, because this angle in here is actually equal to alpha as well. So that's alpha in there, and I'm sure you've seen that before and it's easy enough to prove. What that means is that this perpendicular force is going to be the cosine of this triangle. So if you think of this triangle here as kind of a right angle triangle, then this is the hypotenuse. This is going to be the cosine multiplied by the hypotenuse, and this parallel force is the sine of alpha multiplied by the hypotenuse. Okay, I'm sure that's all pretty standard for you. Then what we also have is the normal force, which is the equal and opposite to this perpendicular force. And what I usually label these is W1 and W2. So what that tells me is they're the components of the weight. So the weight is what we call the force due to gravity, and these two, W1 and W2, are the components of that force. Now we know this particle has been propelled up the slope, but it's no longer being pushed up, so there's not an active force pushing this particle up the slope. But we do know it is moving, so this is the direction of movement up the slope due to this force that was applied, somewhere further down. So if movement is going up the slope, that means we have a component of friction moving in the opposite direction to the movement. So this is getting a bit messy, but I hope it's still clear enough. That vector there is representing the force due to friction. So hopefully that's kind of helping you picture what's going on. What it tells me is that we don't have any force going up the slope, but we have the parallel force acting down the slope and the force of friction also pushing that way. So what I can say from this is that the net force will be the frictional force plus W2. Now if you use different notation for some of these things, that's fine. Please keep using the notation you're comfortable with. So this equation is hopefully going to allow us to solve it for mu when we substitute in the different values for these things. We do have a formula for the frictional force, which says that the frictional force is mu times the normal force. So the normal force is the equal and opposite to the perpendicular force, so that would be going up. Let me just draw that in different colors so it's not too confusing. That goes up here. That's the normal force. Okay, so let's go back to this equation now and start seeing if we can fill some of these details in. Now, the net force is always the mass times the net acceleration. Now, they've actually given us that in the question. They've told us the constant deceleration is 4/5g. The frictional force, as we've said, is mu times n. And W2 is the parallel force, or mg sine alpha. All right, good start so far. Now, if you're being really technical about this, you would actually say that these are all negatives, because we're talking about deceleration. The frictional force is acting down the slope, and the parallel force is also acting down the slope. So all of these, if you're being really precise, they should all be negatives. But in the next step, you can just divide by -1 to make it slightly easier on yourself. I find it always easier to work with positives than negatives. So maybe it's a good idea to put that step in to show that you understand the direction of these forces. Now, before I start trying to substitute things into this equation, I'm going to rearrange it so that I have mu by itself on the left-hand side. So what I'm going to do is actually subtract mg sine alpha from the left-hand side and then flip it around. So what I'll end up with is mu n
equals MA take mg sine alpha. Okay, and then let's think about this n. N, remember we said is mg cos alpha, so we can substitute that in now. And I'll leave the right hand side as is for now. Okay, sine alpha, and then we've got the mass on the left and the right hand side, so they'll cancel out. And then what I want to do is to get mu, as I said, by itself on the left hand side. So divide by g cos alpha, and then on the right I'll have a minus g sine alpha divided by g cosine alpha. Alright, this is looking good. I'm trying to solve for mu and I have an equation for mu. Now I need to try to substitute the values in here. Now I have a, the deceleration, which was 4 on 5g, and I need to work out the sine alpha and cosine alpha. Luckily in the question, remember they tell us tan alpha equals 3 on 4, so we're going to be able to use that fact to find sine alpha and cosine alpha. So let's just draw a quick right angle triangle to illustrate what I'm talking about. Alright, so here's our little right angle triangle. We've got alpha in the corner, and we're told that tan alpha equals 3 on 4. Remember the ratio for tan alpha, that's opposite over adjacent. We need to use our trigonometric ratios here to solve this. So tan alpha is 3 on 4. That means that the opposite side, this is the opposite, this is the adjacent side. This is going to be 3, this is going to be 4. And you could use Pythagoras' theorem if you need to figure out that that hypotenuse must be 5. And then use the other ratios. So sine is opposite over hypotenuse, so that's going to be 3 on 5. And then cosine alpha is adjacent over hypotenuse, so that's going to be 4 on 5. Okay, so we have values for sine and cosine alpha. Substitute those in as well, so this is going to be 3 on 5 and g times 4 on 5. Okay, do you notice what we can cancel here? Yep, the g's, so the acceleration due to gravity is the same in all cases, so that's going to cancel itself out. And what we're left with is 4 on 5 minus 3 on 5 divided by 4 on 5, which we can easily solve. So 4 on 5 take 3 on 5, that's 1/5 divided by 4/5. 1/5 divided by 4/5, that's going to be 1/4. So we end up with mu equaling 1/4, and we're done. So that's the coefficient of friction. Okay, back to the question. The particle comes to rest at the point A on the plane. Determine whether the particle will remain at A, carefully justifying your answer. Okay, so let's have a go at B down here. So let's just figure out what's going on with a quick diagram again. So the particle, remember, was moving up the slope, and those forces were acting on the particle, and now it's come to rest. So it's now at rest. So what happens to the friction of a particle at rest? Well, it actually pushes in the opposite direction. So now friction will be going in this direction, and the force due to gravity, or the parallel aspect of that, will be pushing down the slope. So this was W2. Okay, so we already know what those are. So the force due to friction, we said, was mu mg cosine alpha, and we can figure out what that is. We know mu, that was 1/4. We know, let's not worry about mg for now. We know cosine alpha was 4 on 5, so this would equal 1/5 mg. Now let's talk about W2, or the parallel force. This was mg sine alpha, and sine alpha was 3 on 5, so this would be 3 on 5 mg. Okay, so let's compare these. So we've got the friction force of 1/5 mg and the parallel force of 3 on 5 mg, obviously W2 is greater than the frictional force. So what does that mean? If the force pushing down the slope is greater than the one pushing up the slope, that means the particle is going to start moving down the slope. So we could say something like the net force is pulling the particle down, therefore the particle will begin falling down the plane. I might just add a bit at the start to say no, the particle will not remain at A. So no, the particle will not remain at A, etc. Okay, so that was question 7 for a total of 8 marks. Question 8 starts off with a note and it says, in this question, I and j are horizontal unit vectors due east and due north respectively. And the question goes on, a radio-controlled model boat is placed on the surface of a large pond. The boat is modeled as a particle. At time equals 0, the boat is at a fixed point O and is moving due north with speed 0.6 meters per second. Relative to O, the position vector of the boat at time t seconds is r meters. At time equals 15, the velocity of the boat is 10.5 I minus 0.9 j meters per second. The acceleration of the boat is constant. And part A says, show that the acceleration of the boat is 0.7 I minus 0.1 j meters per second squared. Okay, so let's have a go at that down here. So we're given velocities and time, and we're going to have to be able to use that information to find acceleration. So I'd start off with acceleration equals the change in velocity divided by the change in time. That's a pretty good place to start. And we know the change in velocity equals the second velocity, or v1, minus the original velocity, v0. So we know the velocity at t equals 15, 10.5 I minus 0.9 j. And we know the original speed was 0.6 meters per second due north. And remember they said j was the north vector, the vector pointing in the north direction. So this is going to be 0.6 j. And then we can simplify this. So we've got negative 0.9 j, subtract 0.6 j. That's going to be 10.5 I minus 1.5 j. So that's our change in velocity. And we know the change in time, they told us that in the question, is 15 seconds. So now we can just go ahead and calculate the acceleration as 10.5 I minus 1.5 j divided by 15. And well, this is like 105 divided by 15, so that would be 7, so 0.7 I, and then this must be 0.1 j. And that would be in meters per second squared. So let's just check. Yep, that's what we want to show, and we've shown it. So there we go for part A. Part B says find r in terms of t. Remember, r was the position of the boat, so we need an equation for the position in terms of t. Okay, so let's get started on part B. So I'd start with this equation. The position, or r in this case, is equal to vt plus half at squared, sometimes referred to as position or displacement, and this is usually v0, so the original velocity times time. Okay, so we know the original velocity was 0.6 j times t, and we know the acceleration because it's constant, so the constant acceleration is 0.7 I minus 0.1 j, and then t is, well, we're looking for it in terms of t, so we can leave t as is. And that's all they're looking for in that question. As long as you can use that formula and substitute everything into that formula, you've got r in terms of t there. Okay, back to the question. Part C says find the value of t when the boat is northeast of O. So C, maybe we can fit C in here. Anyway, so when northeast, the I and j vectors will be the same. So when they refer to northeast, they're talking about a 45-degree angle exactly from north and east. Anytime the boat is 45 degrees from both north and east, then the I and the j vectors will be equal length. I'll just state that. So I and j vectors have equal magnitude. We know from part B that the position R is equal to 0.6 j_t plus a half 0.7 I minus 0.1 j_t squared. Firstly, I'll just simplify this a little bit. So expand these brackets out. So this is just going to be 0.35 I minus 0.05 j. And also we have that t squared belonging to both. Okay, I should have moved it down the page. Now what I might do is factorize out a t. So 0.6j, I factorize that out, plus 0.35 I t minus 0.05 jt. And remember we said the I and the j vectors needed to be equal. The only way we can have these magnitudes to be equal is to find an appropriate value for t here. So what I want is for the magnitudes in here to be equal. So I want this 0.6 subtract 0.5 times something equals 0.35 times something. So I can solve that easily because I've just got one unknown in there. So my equation in order to solve that would be 0.6 minus 0.05 t equals 0.35 t. And then I just need to go ahead and solve that. So add that to the other side, 0.6 equals 0.35 plus 0.05 t. 0.6 equals 0.4 t. So therefore t equals 0.6 divided by 0.4, that's 1.5. Okay, so let's just double check the question. They want us to find the value of t when the boat is northeast of O. So what we said was when the boat's northeast, I and j vectors have equal magnitude. We came up with an equation and we solved for t for when those magnitudes would be equal. And we ended up with a time of 1.5 seconds. Okay, so that's part C. Part D says find the value of t when the boat is moving in a northeast direction. All right, so part D, let's start that down here. Now for this one, we can say when traveling in a northeast direction, the magnitudes of the I and j velocity vectors will be equal. Another way of stating that is to say the velocity will equal xi plus xj meters per second. So the magnitudes of these I and j velocity vectors will be the same. And remember, in this one for position, we were talking about position vectors. In this one, we're talking about velocity vectors. So the same principle will apply to this question, just a slightly different equation. Okay, so we'll start off with the velocity formula, which is actually the integral of the position formula, which says that the velocity equals v0 plus at. Now we know the starting velocity was 0.6 j. The constant acceleration was 0.7 I minus 0.1 j. And we're going to solve this for the t here. And this is meters per second. So let's go ahead and make an equation out of this like we did last time and solve it for t. So we've got this 0.6 minus 0.1 t, and that needs to be equal to the magnitude of the I vector, so 0.7 t. And again, we want the t's on the right hand side, so 0.6 equal to 0.7 t plus 0.1 t. That's going to be 0.8 t, so therefore t is going to be 0.6 divided by 0.8, which gives us a time of 0.75 seconds. So actually we're talking about less than 1 second for the boat to be traveling in a northeast direction. Okay, so that was question 8 for a total of 10 marks. Question 9 gives us a diagram, and it says a uniform ladder AB of length 2A and weight W has its end A on rough horizontal ground. The coefficient of friction between the ladder and the ground is 1/4. The end B of the ladder is resting against a smooth vertical wall as shown in figure 1. A builder of weight 7W stands on the top of the ladder. To stop the ladder from slipping, the builder's assistant applies a horizontal force of magnitude P to the ladder at A towards the wall. The force acts in a direction which is perpendicular to the wall. The ladder rests in equilibrium in a vertical plane perpendicular to the wall and makes an angle alpha with the horizontal ground where tan alpha equals 5/2. The builder is modelled as a particle and the ladder is modelled as a uniform rod. And part A says show that the reaction of the wall on the ladder at B has magnitude 3W. Okay, quite a lot of information to take in there. They've already labelled this angle and the length of the ladder. I just wanted to point out a couple of things. So when it says the ladder rests in equilibrium in a vertical plane perpendicular to the wall, that's just meaning that it's not moving sideways. So it's not shifting kind of that way, you know, like off to the side, if that makes sense. So it's not going this way type of thing. It's hard to draw with arrows, but basically we're looking at a two-dimensional movement rather than three-dimensional sideways. And we have the weight of the ladder, W, and the weight of the builder. So the builder is at B, and his weight is going to be a vector from B. And the weight of the ladder, when we have a long length like this, it says to assume that it's a uniform rod. So the weight is going to be from the middle of that. And we're looking to prove that the reaction of the wall is 3W. So this is going to involve looking at torque or moments around a point, and this is to do with the idea of a pivot. So if you think of maybe a seesaw, for example, it has a balance point or the pivot point, and when that length is balancing, the forces at the pivot point are 0. So whatever forces are pushing up or down here, they balance to 0 at the pivot point. So on this ladder, we have a pivot point at A. So the ladder is going to pivot around that point because we have someone standing there holding it still. And what we can do to show the force pushing from the wall is to take all of the forces at A and make them equal to 0, and then we'll hopefully be able to solve for this force. So let's go ahead and label a few things here. Firstly, we have this weight of the ladder in the middle of the ladder there. Then we have the weight from the builder at the top, and that was 7W. And then we have this force we're trying to look for pushing back from the ladder, because obviously the ladder is pushing against the wall, and we'll have an equal and opposite force pushing back against the ladder. And that's what we're trying to find. Now, a couple other things we can write in here. So we know the length of the ladder is 2A, so we want to be able to find these vertical and horizontal lengths. And we can do that in relation to alpha, because I've told us that tan of alpha is 5/2, and that will come in handy later on when we're trying to solve the equation. But for now, we can say this vertical length is the hypotenuse, which is 2A, multiplied by sine alpha. So that's standard right angle trigonometry. And for the horizontal length, that's going to be the cosine of alpha. And now we should have enough information to go ahead and solve this. Now, some of the rules around moments around a point tell us that in order to shift these force vectors to the pivot point A, we need to multiply them by the length, the perpendicular length they are away from that point. So for example, if I want to shift this force vector at B to A, I need to shift it the horizontal length to A. And I do that by multiplying by that length. So let's get started down here anyways. We've done enough work on that diagram for now. So what we want to talk about is the moments around A, or the force vectors around A. Because the ladder is in equilibrium, or it's not slipping, that means the forces at A are 0. What we can say is that the force due to the builder at A will be 7W multiplied by 2 cosine alpha, plus the force due to the weight of the ladder, which was W multiplied by A cosine alpha. Why just A? Well, remember this weight is in the middle of the ladder. We don't have to move it the full distance, we only need to move it half this horizontal distance, which is going to be half of 2A cosine alpha, which will just be A cosine alpha. And then we subtract this force pushing back from the ladder, which we're looking for. So let's just say that's some force multiplied by the vertical distance. So the vertical distance was 2A sine alpha. So this was this one here, and we shifted it down 2A sine alpha, so we need to multiply it by that length to get to A, and all of those forces should add up to 0. Okay, so now hopefully this equation allows us to solve for this force pushing against the ladder. We can start off by rearranging this and factorizing a few things on the left hand side here. So I'm going to factorize an A and a cosine alpha out of these two. So I'll be left with 7W times 2 plus W equals, and I'm adding this to the right hand side, this will be equal to F times 2A sine alpha. And then if I divide the right hand side by A cosine alpha, I'll be left with 7W times 2 plus W. Well, this is going to be 14W plus W. And on this side, I've got F times 2A sine alpha divided by A cosine alpha. And then on the left hand side here, of course, I've got 15W. And then on the right here, we can cancel a few things. So these A's will cancel out. And sine alpha over cosine alpha, that's tan alpha. So over here, I've got 2 times the force we're looking for times tan alpha. Remember, we have a value for tan alpha. It's 5 over 2. So I've got 15W equals 2 times F times 5 on 2. These 2's here will cancel out. So on the right hand side, I'm just left with 5F. See if we can finish this off on this page. This will be 15W equals 5F, and then therefore F will equal 15W divided by 5. That's going to be 3W. Okay, so there we have shown that the force pushing back on the ladder from the wall will be 3W. Okay, part B says find in terms of W the range of possible values of P for which the ladder remains in equilibrium. Okay, let's just quickly go back to the question again. So P was the horizontal force applied to the ladder at A. So that was by the builder's assistant up here. He was applying some force P this way, and we need to figure out the range of values for that to keep the ladder in equilibrium. The other thing they tell us is the coefficient of friction is 1/4, so that's going to come in handy as well. And so let's get started on part B. So the first thing we can state is that the normal force due to the weight, so that remember the normal force is the opposite to the force of gravity, basically, due to the mass. So that's going to be an equal and opposite force to the force due to the weight, which is just these two weights added together. So 7W and 8W. So we're going to have a normal force of 8W. That's the first thing we can state. So the normal force is 8W. And what we're going to use to solve this is the fact that the frictional force is equal to the coefficient of friction multiplied by the normal force. This is going to be 1/4 times 8W, which is 2W. Now, interestingly, this frictional force can actually act towards the wall and away from the wall, which changes how much force the builder's assistant will have to use. So remember, we have the force pushing against the ladder of 3W. So let's start off with the P max, the maximum force he would have to use. So that would mean this frictional force is pushing away from the wall, adding to the reaction force pushing against the ladder from the wall. So this would be 2W plus 3W, 5W. And the P min would be if the frictional force is helping him against that force pushing on the ladder. So we'd have 3W subtract 2W, which would just be W. So we have a minimum of W, max of 5W, so therefore the range is going to be anywhere in between those. And it can also equal that. Okay, so that was the range for B. And part C says, often in practice, the builder's assistant would simply stand on the bottom of the ladder. Explain briefly how this helps to stop the ladder from slipping. Okay, so let's have a look at the diagram again. So instead of pushing this way, he might stand on the ladder. So therefore he'd be adding more weight, which means there'd be a higher normal force. And if the normal force is higher, the frictional force will also increase because they're directly proportional. So by increasing the normal force, the frictional force will increase as well. So I'll just go ahead and state that as best I can in writing. So as frictional force equals mu times n, if you increase n, then the frictional force increases in direct proportion. Increased frictional force will oppose the force pushing from the wall. So part C was 3 marks. I hope I have enough detail there, but that should be the main idea of the answer. And that was question 9 for a total of 13 marks. Question 10, the last question on this paper. It starts with a diagram and it says a boy throws a stone with speed u meters per second from a point O at the top of a vertical cliff. The point O is 18 meters above sea level. The stone is thrown at an angle alpha above the horizontal where tan alpha equals 3 on 4. The stone hits the sea at the point S, which is at horizontal distance of 36 meters from the foot of the cliff, as shown in figure 2. The stone is modeled as a particle moving freely under gravity with g equal to 10 meters per second squared. And part A says find the value of u, the initial speed. Let's firstly break down this diagram a little bit. So we've got our stone up here thrown at some speed u, and we've got this angle alpha in here. Now this information here, this tan alpha equals 3 on 4, that's going to be crucial to our solution. But what you can note about an object thrown at some angle is that you can break that down into a horizontal and a vertical vector. So this angled vector we can break down into, that's meant to be a right angle by the way, not a very good one, but you can break that down into vertical and horizontal vectors, and that's going to allow us to solve for u. So the way we're going to solve this is to break this down into the horizontal distance and the vertical distance traveled and use formulas for that and kind of solve it like a simultaneous equation. So the final vertical position in relation to the sea level is going to be the initial vertical height plus the initial vertical velocity times t plus whatever acceleration is acting on the stone. So that's going to be acceleration due to gravity. And that's going to end up negative. But for now, I'll just write that as a positive equation. And the final horizontal position is going to be the initial horizontal velocity multiplied by time. Now, I don't need to worry about the XO, the initial horizontal position, because that's 0. We're assuming this is like the origin. We're starting at x0 equal to 0. So let me just write that in so it's really clear. So x0 is 0, so we don't need to worry about that in the equation. And also, there is no horizontal acceleration. So the only acceleration acting on this stone will be gravity. So we don't need to worry about acceleration in this equation. All right, so we've got our two equations for the final position. And what we're going to end up doing is to rearrange the horizontal position equation, substitute it into the y position equation, and then hopefully solve for the initial velocity. But firstly, we need to start substituting some things into these equations. So firstly, what we can say is the final x position we know is 36. I've told that in the question. So it's gone from x0 to x equals 36. So we can substitute that in. The initial velocity along the horizontal axes, I've kind of talked about that already. So we know that tan alpha equals 3 on 4. Remember, tan alpha is the opposite over the adjacent side. So this is going to be 3 on 4, the ratio of those sides. That means the hypotenuse will be 5. And of course, that doesn't tell us the actual size or magnitude of that vector. It's just the ratio, but that's all we really need for now. So we can also find, therefore, the cosine of alpha and the sine of alpha. So cosine of alpha adjacent over hypotenuse, 4 over 5. And the sine of alpha opposite over hypotenuse, 3 on 5. So for Vox, we can say this will be the initial velocity multiplied by cosine alpha multiplied by t. So then we've got 36 equal to VO multiplied by 4 on 5 multiplied by t. Then we want to rearrange in terms of t because we're going to end up substituting that t into this equation over here. And then, so we need to get rid of all of this VO multiplied by 4 on 5. So multiplied by 5, divide by 4. Well, dividing by 4, that'd be 9 times 5, that'd be 45. So we'll have 45 divided by VO. Okay, so now we're going to have to start with the y position equation and see what we can do with this. So at the final position, this y here, the height is 0 above sea level. So here y equals 0. So that's the first thing I'm going to substitute, y equal to 0. And then y, the initial height was 18. Remember, we started at the top of this cliff, y equals 18. So that's going to be 18. And we can do the same thing for this initial vertical velocity. Remember, we said that was sine alpha equal to 3 on 5. So this one here is going to be VO multiplied by sine alpha times t plus half g t squared. I'll just leave those for now. Let's keep substituting things in now. So 0 equals 18 plus VO multiplied by sine alpha. Just again, sine alpha, that was 3 on 5 multiplied by t. And when I get to this t, I want to substitute in our equation over here from the horizontal position. So this was 45 on v. And remember, we said the acceleration due to gravity, that's actually going to be a negative. So we can change that to a negative now. To be honest, this is kind of like my working out. If you want to make it a negative from the start, that's perfectly fine. This is just how I do it. So half g, remember we need to assume g is 10 meters per second squared. So half of 10, that's going to be 5. And then when we get to this t squared, again, I'll substitute in our equation for t. So this is going to be 45 squared divided by VO squared. All right, looking good. Now we have an equation with only one unknown, and we're going to be able to solve this for VO, or in the case of this question, we need to call this initial speed U. So let's go ahead and keep simplifying this. Now, in this part here, you'll notice we have this initial speed VO on the top line and on the bottom line. So we can cancel those out and we can simplify it a little bit. So we'll have 0 equal to 18 plus 45 divided by 5 multiplied by 3, that's 9 times 3, that's 27. Subtract 5 times 45 squared. Let's just leave that as is for now. Divided by the initial speed squared. So I'm going to substitute in a u for that VO now to make it more consistent with the question. And then let's keep simplifying. 0 equal to 18 plus 27, that'll be 45. And now with this u squared, I don't want that as a denominator. I want to get rid of that denominator. How do I get rid of a denominator? Multiply everything by u squared. So this is going to be 45 u squared, and 0 times u squared is just 0. And then over here, I'm just left with 5 multiplied by 45 squared. Okay, this is looking really neat now, almost there. I could divide everything by 45, so I just have u squared by itself. So let's continue on the next page. 0 equal to u squared divided by 45, and then 45 squared divided by 45 is obviously 45. 45 times 5, that's going to be 225, so negative 225. And then take that over to the other side, so add 225 to 0, and we'll get u squared equal to 225. And then take the square root of both sides, so the square root of 225 is 15, so that's going to be 15 meters per second for our final answer. So that was part A.
Part B says find the speed of the stone when it is 10.8 meters above sea level, giving your answer to two significant figures. So the first thing we need to figure out is how far it's fallen. If it started at 18 meters, then it's fallen 7.2 meters. And to find the overall speed, we're going to break this into a vertical and a horizontal vector as we did before. So let's get started on B down here. So the horizontal vector is pretty straightforward because we don't need to consider acceleration. There's no acceleration along the horizontal plane, so this is just going to be u cos alpha. And u is 15, cos alpha is 4 on 5. So this is going to be 12 meters per second. The vertical velocity is a little bit more complicated. We're going to need to use the formula vy squared equals vo y squared plus 2gs. And that can be derived using the basic velocity and average velocity formulas. So for that, firstly we need voy, and that is u sine alpha. So that's going to be 15 times 3 on 5, which is 9. So this is going to be 9 squared, which is 81, plus 2 times gravity, which is minus 10, plus the displacement, which is minus 7.2, as we said. So 81 plus 2 times 10 times 7.2, that's 144, and those negatives cancel each other out. So Vy, or the vertical vector of the velocity, is going to be the square root of 225, which is 15. Okay, so now we have the horizontal and vertical vectors. We can work out the speed using Pythagoras. So I'll just draw a quick diagram to show what I mean by that. So the stone is falling down this way, like that, and we have the vertical vector 15 and the horizontal speed is 12, and we need to work out this hypotenuse using Pythagoras. So the speed is going to be the square root of 12 squared plus 15 squared, which is the square root of 369. And if we put that into a calculator, square root of 369 is 19.2, approximately 19.2. And it asked us to round to two significant figures, so this is going to be 19 meters per second. So that was part B. Part C says suggest two improvements that could be made to the model. So they've used 10 meters per second squared for G. They could use 9.8. And it's a rock traveling through air, so they could also factor in air resistance. So they're going to be my two improvements for those two marks. There are others that you might be able to think of, but they're the two that I'm going to use. So let me just write those down. So use a more accurate value for G, e.g. 9.8 meters per second squared, and factor in air resistance. Okay, so that was question 10 for a total of 13 marks, and that was the end of this paper. I hope you found this video useful. If you did, please leave a like and subscribe if you want to see more content. Please let me know if there's any questions I didn't go into enough detail on. If there's anything you're still unsure of, leave a comment or even email me. And I'll see you in the next one. Bye for now.